So, dear students, I welcome you for the lecture series of chemical equipment design. Today, we are going to discuss the second section of storage tanks, that is related to the different types of storage tanks. That is, one is a floating roof tank in which the roof that is floating, the roof which is floating. Next one is a fixed roof type. Then there are the underground tanks. That is, the tank itself is built underground. That means 90% of the tank is underground. That is for the purpose of maintaining the temperature. Temperature variation is minimized in such underground tanks. Then now we will discuss the different types of the roofs related to the tank. The different types of roof that can be used for the storage tank are vapor lift roof, floating roof, self-supported roof, column supported roof. These are the four types of the roofs which is used for covering the storage tanks, covering the cylindrical storage tanks. Now for the vapor lift roof is, the word itself tells that due to the vapors, the roof that is lifted. Now you can see the figure here, which is the vapor lift roof. A is a vapor lift roof, which is here. This is what the roof which you can see. Basic tank is this thing. This is the basic tank which is available, and to this basic tank I am going to attach a seal tank. This is the J. This is what the seal that will be provided. This is again the seal that will be provided, and there is a moving shell and a fixed tank shell. Now this is what is a fixed tank shell. This is the fixed tank shell, and in between this fixed tank shell and the seal tank there is a moving shell which is attached. This moving shell that is attached to the vapor lift roof. That means because of the vapors which are available here, the roof that will be lifted. So in this construction, roof normally rests on the usual roof support as in the fixed volume cone roof tank. These are the simple cone roof tanks, and certain modifications related with the seal tank and the moving shell that is available. When the volume of the vapor is increased due to the rise in temperature, or when the liquid is pumped, the roof rises vertically, increasing the vapor space. So because of this vapor space, this roof that moves upward. Vapor lift roof adjusts its position depending upon the vapor volume. So the liquid seal is provided at the junction of the roof and the shell. This is what the liquid seal that will be provided at the junction of the roof and the shell, roof and the fixed shell. to prevent the losses of the vapor. So vapors will not be able to go out from here because the liquid seal that will be available here. So this seal is designed to relieve the excess pressure if the relief valve fails to operate. That also is possible. A seal tank J, which is what I have explained, seal tank J, then fixed tank shell K, and the moving shell B that is there. So the liquid seal prevents the loss of vapor at the junction of the roof and shell. It involves a simple mechanism. At the volume vapor increase, roof moves upwards, and as the volume of the vapor decreases, roof moves downward. Then next is a floating roof type. Now these floating roofs are for the liquids having the high vapor pressure. These are used specifically where the vapor pressure is high, that means lower boiling liquids, and which are vulnerable to the fire hazards. These are capable of withstanding the fluctuations in the pressure. So now what happens in this floating roof tank? There is a basic shell which is available. Then the C, that is your roof which is available. This is the pontoon type floating roof which is available. Now this floating roof moves its position, and it is an adjustable pipe support which is provided to this pontoon roof. And this F, that is the hose drain which is available to remove whatever the fluid which is above this pontoon roof. So this is the actual floating roof with certain trusses structure, the details of which we will see in subsequent lecture. This pontoon roof moves up and down depending on the liquid height. So in this type of variable tank, the roof is not supported either by the shell nor by the columns. So this roof that is not supported at the shell, this is what the shell is. It is not supported at the shell. This is actually the shell. So in conical roof, you get this support on the shell, resting over the shell. However, this is a floating roof. So the roof that flows on the liquid itself. The roof is not supported either by the shell or by the columns, but meant to rest on the liquid, stored liquid, and is free to move with the level of the liquid. That means what is the level of the liquid? The roof is going to move up and down. As this roof that rests on the surface of the liquid, so there is no vapor space. So vapor space is negligible, and as a result the breathing losses are also negligible. Since there is a little space in which the air vapor mixture that can be formed, so it is difficult to create the perfect seal between the floating. Therefore, the certain amount of the liquid is lost through the imperfect seal, means the clingage losses will be observed here. Clingage losses is what? Which is the liquid adhere to the surface of the wall. To this wall surface, the liquid that will be adhered. To this wall surface, the liquid that will be adhered. So when this floating roof that moves downward, this surface is with a certain liquid droplets, and as a result the evaporative losses from the adhered liquid that will be observed. However, the breathing losses are negligible in this floating loop, but the clingage losses are prominent in this floating loop. Now, in this floating roof, there are the different types, that is the pan roof, pontoon roof, and double deck roof. So, this pan roof, it is the cheapest roof as compared to the other roofs. It is provided with an upstanding rim at the periphery, which gives it floating characteristics. That means at the periphery, the certain rim that is provided here at the periphery of the roof. Since the pan is a single deck roof, unchecked leaks through this deck will eventually cause to sink. If certain leakages are there, if certain leakages are there on this roof, the because of its weight, this roof may sink. It has no other buoyancy other than that provided by the deck and the rim. If the roof is locked with the rain and snow, the rim gets compressed and begins to deform. Excessive desolation can cause an imperfect seal. Nantar, there are the different types of the pan roofs. The trussed pan roof. This is what the first figure is related to the trussed pan roof. Then second is the pan roof with center weight which is provided. Then the underdeck trusses. These are the underdeck trusses. And next is the with underdeck girders. With underdeck girder that is provided. This underdeck girder that is provided. So there are four types of pan roofs. That is the truss pan roof with center weight, pan roof with underdeck truss, and with underdeck girder. Now next is a pontoon roof. However, in case of pontoon roof, this area that is increased. That is, this represents the significant improvement over the pan roof. The buoyancy and the stability are increased. It acts as a insulator or helps in insulation of product from the sun rays. As a result, these roofs are widely used in both cold and hot climates. It is used for corrosive and non-corrosive product with vapor pressures up to 1 kg per centimeter square. It can trap vapors under this single deck. Certain vapors that can be trapped under this deck. Slight vapors that can be accommodated in this. So there are the different types of pontoon roof. Pontoon roof with central weight. This is with central weight. Then pontoon roof covering 50% of the roof area. This is up to 50% of the roof area that is covered. Then this is your standard pontoon roof, the normal standard pontoon roof, and pontoon roof with deck raised off product. Pontoon roof with deck raised off product. प्रोडक्ट के ऊपर एक्चुअल रूफ आएगा ये. Then next is a double deck roof. This roof comprises of upper and lower decks separated by the bulkhead and trusses. Now in this figure you can see the two roofs. One is this upper roof and second is this roof which you can see. So these are the two roofs. One is the upper roof and second is the lower deck. The circular bulkhead drives the entire roof into the annular liquid tight compartment. The radial stresses are dispersed through to provide the required strength and stability because of its superior load capacity and insulating characteristics. The double deck roof are extensively useful for all types of the products in all climates. That means these roofs, they are two, as the two decks are available, one is the upper deck and lower deck, and this lower deck which is moving up and down. Next is a self-supported roof. This is the basic self-supported roof which is available. So these are the self-supported roof, that is the conical roof. Self-supported conical roof. That means any tank which is the conical roof that is resting on this shale. So this is your shale and this conical roof that rests on the shale. This is the self-supported roof. In this type of the roof, the entire roof load is supported by the tank periphery without the support of the columns. Only the shale periphery that is used to support. These self-supported roofs are used up to the 12-meter tank diameter. That is what the limitations are there. If the tank diameters are more, then the certain column supports they are provided. The roof shape may be different. That is, you can have the cone roof, the dome roof, or the umbrella roof. That is simple conical roof, or the dome type shape is provided, or the umbrella type shape that is provided. Now when this is a cone roof, then what should be the slope? Then the appropriate to the surface of the right cone is 1 in 5 or 1 in 6. This is for the slope that is provided, 1 in 5 or 1 in 6 that is generally provided. Then dome roof, the radius of curvature is spherical radius. And then related to the umbrella roof, it is modified from form of a dome roof and is formed in such a way that any horizontal sections is regular polygon. Now how to design this self-supported roof. This is the most simplest form to design the self-supported roof. The stresses in the cone roof plate are determined by considering the load, that means F, which is equal to PD upon 2T sine theta. This is our PD upon 2Fj, the same formula. Thickness which is equal to PD upon 2Fj. Here is certain angle theta that is provided. So F is the stresses of the roof plate, P is the pressure due to the roof loading, then D is the diameter of the cone roof, T is the thickness, and theta is the angle between the cone roof and the horizontal. Then the critical compressive stresses that can cause the failure of a plate due to the wrinkling is given by, this is the critical compressive stresses, 1 upon lambda into E upon 3 into bracket 1 minus mu square raised to 1 by 2 into T by R. R is nothing but your diameter by 2. Then the same thing, lambda is your factor of safety. For safe compressive stresses is taken with a factor of safety lambda, which is 12. So lambda, that is replaced by 12, and mu, that is Poisson's ratio for stainless steel, it is 0.33. So after simplification you get theta sin theta, which is equal to d upon t into p upon 0.204 into e raised to 1 by 2. The slope of cone, that is tan theta, is limited to 1 in 5 or 1 in 6. Tan theta is limited to 1 in 5 or 1 in 6, from which the plate thickness is determined. So ultimately what is there? You have to determine the plate thickness of a roof, plate thickness for the shell. So we are finally designing the thickness of a storage tank, the shell thickness and the roof thickness and the bottom thickness. Now the roof curve angles are there. These are nothing but the structural angles which are welded to the top of the shell. Welded to the top of a shell. These roof plates of the tank rest over these angles. That means to this shell, certain angles they are welded so that my roof that will be raised over that. Here also I am going to provide a certain angle which is welded. Then it will be resting on this roof. So these are the roof curve angles. These are your roof curve angles which are welded to the shell and gives the support to the conical roof. So roof plates of the tank rest over these angles and are welded to the shell. Roof curve angles act as a compression ring because all the load of this roof that will be resting on this angle. The angles are welded with a square butt joint. The minimum dimensions of the roof curve angle depends on the tank diameter. So depending on the tank diameter, if tanks up to the 10-meter diameter, it is generally 65 by 65 by 6 millimeter angle that is used thickness. So 65 is the length, 65 is the width. However, the thickness is the 6 mm thickness of this angle that will be there. So depending on the tank diameter, the thickness and the length and the width of the angle that is going to vary. Then what are wind girders? That is also there. Now looking at this figure, it is the actual view of a storage tank. So this storage tank, you can see the number of plates that are welded to form the vertical structure of a shell, and here the certain wind girder that is provided and it is supported with a certain structural sections. So this is what the wind girder and the structural strength supports that will be provided. Means on this structural support, on these angles, the wind girders that will be provided. So these are the different structural supports, and these structural supports are nothing but your certain angles. So these are all your angles. This is what the shell is, and this is the structural angle, and this is the bracket that is provided or welded. Here again it is welding that is being done with a metal plate so that it will remain as a rigid part. So this is the wind girder. Now why you require these wind girders? The large storage tanks are provided with the wind girders. Since the minimum thickness is around 5 to 6 millimeter at the topmost portion. In the uppermost portion of a shell, the minimum thickness is around 5 or 6 millimeter, which is minimum required for your welding purpose. The top portion is necessary to be provided with the sufficient strength. So, if the tank is subjected to a certain wind load, it will be disturbed the structure of the tank. It will disturb the structure of a tank. Now, if it is the tank which is provided, if the wind load which is acting here, it's now it is initially a circular more or less. Now I am providing a certain wind load. So what is happening? It is getting deformed. Ovalization. Instead of circle, it will become an oval. That will be deformation that will take place. And so prevent this deformation, I am going to provide this wind girder. That is, the top portion is necessary to be provided with a sufficient strength. As if it is subjected to the wind load, it will try to disturb the structure of the tank, and therefore the stiffening rings, which are known as the girders, they are provided. Now, as they are provided, they will serve the purpose of a reinforcement against the buckling. That means against the deformation. Prevent the reinforcement against the buckling. It also helps to maintain the circularity at the top of a tank. Circularity at the top of a tank, that is to prevent the ovalization. Also, it can be used as a walkway for the roof inspection. These are the simple plates. So, as these are the simple plates, you can walk over that. So, it is considered to be as a walkway, and it is provided generally 1 meter below the top edge of the storage tank. Then the width of this ring should be around 600 millimeters. The width is around 600 millimeters of these edges. These wind girders are fabricated from structural sections of the desired section is fabricated by welding. So these are the different structural sections which are provided, and on this you can walk very conveniently, and it prevents the ovalization or deformation. It provides the strength. So this is the purpose of a wind girder. Now coming to the what should be the optimum size? What should be the optimum diameter to the height ratio? This is done based on your cost calculation. The optimum proportions of this storage tank is determined by the cost considerations. When the quantity of liquid to be stored is less, then this cost doesn't have a significant amount, but as the diameters increases, as the volume increases, the diameter and the height also increases. So this cost of these tanks, that will be the huge, because you have to store the huge capacity. In case of your crude oil, they are very very huge tanks, say of 100 meters, 50 meters, 100 meters diameter, and the tank dimensions height is can be up to the 10, 20 meter, 30 meters height. So huge structures are there. That is, storage and handling of these raw materials have to be safe and should be at a minimum cost. So the minimum parameter that should be considered while determining the optimum proportion of the storage tank. Now D is the diameter and H is the height of the tank. So we will consider what should be the volume of this tank and what should be the area. Now this is what is a shell. This is the roof and this is the bottom of the tank. So you can have a triangular roof also, right? Then what is the volume of the storage tank? The storage tank volume, that is pi by 4 d square into the h. I can write h as 4v upon pi d square. Then surface area of this cylindrical shell. What is the surface area of this cylindrical shell? This is what is cylindrical shell that is available. So what will be its surface area? That is pi d circumference into the height. H is the height. Then the surface area of the bottom section, that is nothing but bottom and the top section, it is nothing but your cross sectional area. Cross sectional area, that is the at the bottom and at the top. This will be your cross sectional area. So that is nothing but pi by 4 d square. Now the annual cost of fabricated cylindrical shell, which is C1, cost of fabrication of this shell is C1. Then the fabrication of a bottom, that is C2. Also remember the area. This is cylindrical shell, means the area is A1, which is pi d into the h. Fabricated bottom, that is nothing but the cross sectional area A2. Then the annual cost of fabrication of a roof. Roof is its area, that will be the same as the cross sectional area. Then the foundation. Foundation, that is also same as the cross sectional area. Bottom जितना है, top roof जितना है, उतना ही foundation है. Then the annual cost of land chargeable to the storage tank on the basis of the tank bottom area. This is again same as your cross sectional area. So C2, C3, C4 and C5 multiplied by the A1, that is nothing but the cross sectional area, and C1 is related to the shell cost. So A1, that is nothing but your cross surface area of the shell. So C, that is the total cost, will be the sum of the all costs, which is pi d sc plus pi by 4 d square into C1 plus C2 plus C3 plus C5. Now depending on the dimensions, that is whether it's a small capacity or it's a large capacity, the certain cost that is going to vary. Cost of the shell, fabricated shell, that is going to vary if the tank size is small and if the tank size is big. So this C1 cost that is going to vary or affect. So in case of small capacity storage tank, uniform shell plate thickness can be used from the bottom to the top of the shell. Uniform shell plate thickness can be used from bottom to the top of the shell. Means throughout the shell, I am using the uniform plate thickness. Throughout the shell, I am using the uniform plate thickness. This is for the small storage capacities. If the product D H in minus 0.3 if less than 1.68 for lap joint, and the product D into H minus 0.93 for the 193 for butt weld joint, then the shell thickness is independent of the diameter and the height. The shell thickness will become the independent of the diameter and the height. So this is all related to the shell. The cost of the shell is going to affect here C1, that is the cost of a shell, and the shell thickness is independent of diameter and the height. So after substitution and then differentiate this cost with respect to the diameter, and for optimum proportion the minimum cost will be the dc upon dd, which is equal to the 0. This is general optimization, that the differential of the cost, you are going to consider the cost and the diameter. So cost that is going to vary with the changes in the diameter, that is the dc is the diameter cost and dd is the diameter. So after differentiation and simplification and substituting the value of V, which is equal to pi d square by 4 into the H, d upon H, that comes out as the 2C1 upon C2 plus C3 plus C4 plus C5. This derivation that comes for the small capacity storage tank where the shell thickness is independent of diameter and the height. Now second part, for large storage tanks where the shell thickness is dependent on the diameter and the height. So again, this is the cost of a shell. So cost of a shell is C1, which is going to affect. So this C1 that will become equals to the C6 into H minus 0.3 into the D. So the annual cost of a shell per unit area is dependent on the diameter and the height. So we have incorporated the height and the diameter in this cost of a shell. So the total cost of storage tank, that is the same as the above equation, A1 into C1 plus A2 into C2, C3, C4, C5. So substituting A1, that is nothing but your surface area of the shell. Substituting A2, that is nothing but your cross-sectional area of the roof, bottom's land cost and the bottom construction. So substitute the value of the H as 4V upon pi d square and then simplify that, you will get this thing. Then differentiate with respect to the D and equate it to the 0. Again, we are going to differentiate dc upon dd and equate it to the 0. So after differentiation, you will get this equation. Then substitute the value of V and C6. Simplification, you will get this equation, and for approximation H minus 0.3 is written as H, because the height is very high. And say for example, if it's the height is 10 meters, 10 meters minus zero point 0.3 is only 9.7, so your height is approximately 10 meter. So this is your 4 times C1 upon C2, C3, C4, C5. So diameter to height ratio, that is coming as 4 times into C1 upon C2, C3, C4, C5. This is applicable for the large storage tanks where the independent of the diameter and the height, where the shell thickness is dependent on the diameter and the height.